Hey everyone, welcome back. We're talking about improper integrals again today. And yesterday we introduced the idea of these improper integrals where let's have a look, where we essentially found the area under an infinite region. So we were looking at a curve that went off to infinity in the x direction, and we were finding, let's say starting at 1, we were finding under the area under the curve going off to infinity. So we're going to get an infinitely big area along on the right there. This time, we're kind of looking in the other direction and we're saying, well, what about if the function's not defined, right? This function that I'm giving here is not continuous at x equals 0. It's not defined at 0. In fact, it goes off to infinity. There's a vertical asymptote. And so what happens in that case? Because I can sort of sketch the picture and look at the area and ask if the function actually has a finite area. Is this red area between 0 and 1 for this particular function, just picking this example, 1 over the square root of x, is there a finite area here? So this is going to be an infinitely large region in the sense of I can't enclose it in a box, right? Because this region is perfectly well defined that way if I'm thinking about this red area, but it's going to go up forever in that direction. So just looking at that red area I've got here, I'm talking about this kind of area. There's x equals 1, here's a boundary there. But it goes up infinitely far there. So because of this vertical asymptote, it never closes completely. So it's a really thin, infinitely big region. And what I want to know is, does it enclose a finite area? Even though the region's infinitely big, and I'm going to call it unbounded, and what I mean by unbounded is I can't put it in a box. Even if it's got a finite area, going back to our first one, this thing had a finite area, but it was an infinitely big region. So I couldn't draw a box, let's do a different color. I couldn't draw a finite sized box that completely enclosed that area. Even though the area was 1, right? There was a finite area of 1, I couldn't put it into a box. The region wasn't bounded. So this second type of integral is similar. The region's not bounded. And our question is the area finite? And that's kind of the question we're asking today. So we can set up an integral, right? Let's set up an integral to do this. I'll move on to the next page where it looks nicer. And setting this up similarly to last time, I can build a well-defined integral that goes from the point b to 1. So you can see the green shaded region here. I'm integrating from b, which is a number bigger than 0, up to 1. And f is continuous everywhere in that region. And remember, if you remember back to Calc 1, that's what's required for the integral to exist. The definite integral exists if the function you're integrating, the integrand, is continuous on that region. So this is well defined, right? This thing here is a well-defined integral. It makes sense. It matches our definitions. We can do it with Riemann sums and all of that stuff. It's fine. And then, like last time, we're going to take the limit as that thing fills in the region we actually want. And the region we actually want is to say, I'm going to take this endpoint b, and I'm going to slide it to the left. I'm going to slide it towards 0. So I want b to be going to 0. But again, I want b to be going to 0 from the right, and so I'm going to take a right-sided limit, right? Because this b is going down towards 0, but it's positive, because that thing is then defined. So that gives us an integral to do. The actual integral is easy. Let's evaluate it. Right? This is just an x to the half, well, x to minus a half integral, and so we end up with that, and then evaluating at the endpoints. We find that this is twice square root of 1 minus twice the square root of b. We end up with this. This is an easy limit to take, right? This limit we can evaluate. Square root of 0 is well defined, so this is 1 minus 0. So this thing is continuous, and so the limit exists. We can just do it by substitution, and plugging it in we get 2. So this red area that I started with here, the area under the curve from 0 all the way to 1, even though the function's not defined at 0, that area is finite. And so this is a second kind of integral where it's improper in the sense that we're integrating up to a point where the function's not continuous. This time. Last time we were integrating an infinite region. This time we're integrating up to a point where the function is not continuous. And we can do it using this limit idea. And we can still get a finite area. Right? And that's the kind of cool thing with these. We've got a finite area. The area is 2. This red area is 2, but it's an unbounded region. In some sense, it's an infinitely big region, not in area, but in terms of how much space it fills. Because it's just going up forever, upwards this way. All right, so let's sort of formalize this. So here's the theorem from the book, and they're describing essentially what we just did. Let's look at the second one first. Let's look at this piece, because this is the case we had. We had a function that was continuous between a and b, but not at the endpoint a. Right? In our case, we had a equals 0. So b was fine. The function was continuous at b, but it's not continuous at a. So we take a limit from the right at a. This second case, we're looking at a function where at this point a, we have a vertical asymptote. So it's looking something like that, and there's b, and we're taking the limit as we head back towards this wall at a where there's a vertical asymptote. And I use b in the limit. I probably should have used an r. The first one just looks at it the other way around, where the function fails to be continuous at, that's a terrible graph, where the function fails to be continuous this time at the point b. So in other words, we're thinking about a vertical asymptote at b, and the function's doing that, and here's a, and there's b, and so the function fails to be continuous at b, and so we take a limit, they're using the symbol r here, there's our r, we do that integral, and then we take the limit as r approaches b, but it's approaching from the right, it's approaching with a negative there. So however we need to set up, in this case the r was here, and we were moving the r back towards a, and it was approaching therefore from numbers bigger than a. So however we do this, we define an integral that makes sense where the function is everywhere continuous, this kind of orangey burnt region, and then we either slide it to the right or to the left. In other words, we slide it towards the vertical asymptote. And we say that the integral converges if the limit exists. So in our case, in the previous one, that our integral converged because it equaled 2. And the fact that it equals a finite number means that it converges, because the limit exists, right? Converges just means the limit exists. And we can use this notation now. As long as when we use this notation, we put the 1 there we put the 0 there even though we know this isn't defined at 0. When we're using this notation, this is what we mean. We mean we're going to take a limit. So that's the idea of these unbounded integrals, the book calls them. They're another kind of improper integral. Let's look at another example. So here's another one. Looking at this, what we need to do is think about where any discontinuities are. So we're going to divide by 0 when x equals 2. So this thing is discontinuous at x equals 2. So we need to use the tools we've just described to think about how this integral works. We're going to need to drop the 2 from the limit, and we're going to approach 2. So the limit as this thing goes to 2, we're going to integrate from 1 up to r, and then then r is going to approach 2 from below, right? We're going to approach, thinking about an x-axis here, we're saying we're integrating between 1 and 2, and whatever the graph looks like, there's a, vertical asymptote here, and so it's going to have this general flavor, and so, you can remember this theorem, but just think about what the picture looks like. Vertical asymptote here, which means we need to drop the 2 from that limit of integration, and then approach 2 from the left. All right, so I'm putting an r there, we're actually doing that integral, and then we're taking the limit as r goes to 2. So plugging everything in here, this piece hasn't changed, and then we can do the integral. If you want to do this by hand, you think about it, the U-Substitution to use is 2 minus x, so du is going to be negative dx, but if you can see how it works, you can just go ahead and do it. This is again going to be the limit as r approaches 2 from the negative, and evaluating it is going to give us 2 minus x to the power of 2/3. Think about differentiating this again. 2/3 comes down, cancels this. So negative from the inside, we're going to be left with the power of negative 1/3, which is what we had there. Right, you can do the U-Substitution down here. And doing the U-Substitution, you'll see how I got that term. All right, so we just evaluate it. Evaluating it, just plugging in the r and plugging in the 1, we're going to end up something like this. I put the minus 2/3 out the front. And so that's going to give us, this has got a bit crowded here, but let's just go back to writing the integral down. That's going to give us a limit to take. And as as r approaches 2 from numbers smaller than 2, this thing's just going to go to 0. So again, we're going to get 0 there, and this limit's going to become minus 3/2 of 0 minus 1. And so we're going to end up with 3/2. The integral here converges. We found it converges by actually calculating its value. If it diverged, we would get something going to infinity, and then we'd just say, okay, that limit doesn't exist. So the integral diverges. Let's have another go. So here's another one, secant squared, integrating that. If you think about that for a second, we can work out what's going on. Cosine, remember, looks like this, and that's pi over 2, and that's 1, and that's 0. And so secant is 1 over that, and then you square it. So if I drew the secant function, if you go and look at Desmos or something, you'll see this. If I draw the secant function between 0 and pi over 2, there has to be a vertical asymptote there, because cosine is 0, so secant is 1 over 0. So there's a vertical asymptote there. It starts at 1. 1 over 1 squared is still 1. So if you think about secant, it must look something like that. And it's going up to this vertical asymptote, right? So this region under here is going to be one of these improper integrals. And the graph I'm drawing here is secant squared. Secant squared of x. And what we need to do is work out that integral. So again, this time we've got an issue with this function at pi over 2. So secant squared is not defined at pi over 2. That's a horrible line. And so we need to break this integral up using the ideas that we've just talked about. So in this case, we're going to throw an r in here, r, and then we're going to integrate it from 0 to r, and then we're going to sweep r over towards pi over 2. So we're going to take the limit as r goes towards pi over 2, and you can see from the graph that pi over 2 is bigger than r, so we're approaching r from numbers smaller than pi over 2. And then we're going to integrate from 0, is that right? Yeah, to r. And we're just integrating secant squared, and we know the integral of secant squared, it's tan. So we can just write that down. So just integrating that gives us a tan, and now we just have to plug in, right? So we get tan of r minus tan of 0, and tan of 0 is 0, so this is just tan of r in the limit that r approaches pi over 2, gee that's horrible, pi over 2, from the right. Right, so we go tan of r, there we go. Well, remember the graph of tan? Here's the graph of tan. So what happens as we approach pi over 2 from numbers less than pi over 2? Right, because our r is there somewhere, and we're approaching pi over 2. So the y value is going to infinity. So this limit doesn't exist. It doesn't exist because it goes to infinity. So this integral diverges. The integral diverges because that limit goes to infinity. And that means that this orange area I sketched up here, there's actually an infinite amount of area under the graph of y equals sec squared, secant squared of x, between 0 and pi over 2. Because that integral diverges. The area just gets bigger and bigger and bigger and bigger as we add more area. Right? Adding more area, I mean we're moving the r value to the right. The r value is getting closer and closer to pi over 2. And as we do that, we're just adding more and more and more area as we approach pi over 2. So that gives you an example of a divergent one. It can also be useful to think about the p integral. So remember we talked in the previous type of improper integral, we were looking at integrals between 1 and infinity of 1 over x to the p. And really we're interested in p's bigger than 0, because then the x is really in the denominator. We can build a version of these because notice that this function is not continuous at 0. So what might be interesting is actually to integrate from 0 to 1 and ask, does that converge? So let's do that next. So here's our fundamental question. For what values of p does that integral converge? Maybe it's for all p. And we can do it by just evaluating the integral. So writing it down and applying our definition for these improper integrals, these unbounded integrals. This thing is discontinuous at 0, which means we need to drop the 0 out of the integration here and then integrate from r to 1 and then take the limit when we're done. So doing that, again, the integral is reasonably straightforward. This is x to the minus p, so we get x to the minus p plus 1 divided by that same value. And again, we're going to ignore p equals 1 because otherwise that would be a problem. And then we need to take the limit. So just plugging in those values and factoring out the denominator there, because it's just a constant, we end up with this. And similarly to last time, what we find is, well, if p is bigger than 1, if p is a number bigger than 1, then this thing is a number in the denominator. As it goes to 0, it's going to diverge. So in this case, it's going to diverge when p is bigger than 1. Right, and the reason for that is because we've got something that's going to look like this. If p is bigger than 1, let's say p was 2, you would be looking at a term like this. If p was equal to 2, that's the term you would get. And if r is going to 0, then 1 over r is going to infinity. So it diverges. But if p is less than 1, then this kind of thing is going to actually be flipped. So imagine p is a half. And we've already seen that case, right? We've already integrated 1 over the square root of x. But if p is a half, then this would become r to the power of, well, a half minus 1. And that's 1 over r to the minus 1 half. And that's the same as r to the 1 half. And so if you take the limit as x goes to 0 for that term, this is one where it's less than 1. If I take the limit as x goes to 0 now, well, that goes to 0. So that whole term goes to 0, and we're left with 1 over 1 minus p. And if we think about the other case, the 1 over x dx, when p is equal to 1, in other words, we're going to get the natural log of x. And we're evaluating that between, well, r and 1, and then we take the limit. And so when we do that, we're going to get the natural log of the absolute value of r. And we know that log of 1 is 0, so that just drops out. And then we're going to take the limit as r goes to 0. Well, log is not defined. In fact, as r goes to, think about the graph of r now, the graph of log looks like that. So as there's our log function, as r approaches 0, that's the limit we're taking, we're heading down the curve this way. So that's heading off to minus infinity. So it's going to diverge in that case as well. So it diverges when p is bigger than or equal to 1, and it converges when p is less than 1, which is the other way around from the infinite regions. And here's the nice summary theorem from the book. I'm just integrating up to 1. They've done r, it doesn't matter. The divergence is all about what's happening near the origin, right? Because we're integrating functions that essentially have a vertical asymptote up here at 0. And so where you put the a doesn't matter. The problem, the infinite area, is coming up there, right? So whether I cut it off here or cut it off there, it doesn't matter, because the infinite area is coming from the peak up really near 0, from the vertical asymptote. So that gives you an idea of those. Let's have a look at one more where we use the comparison theorem. Remember last time in the previous lecture we talked about the comparison theorems, how to compare one integral to another. We can do the same sort of thing here, because now that we've got these p-tests, we know how p-integrals behave. So if we can compare an integral to a p-integral, then we can work out what's going on. So let's just have a look at one of those. Okay, so here's a kind of funky integral. Let's think about that function. I'm not going to be able to integrate it. I don't know how to integrate a function that looks like that. It looks like a mess. But I can compare it to other functions and use that comparison idea to determine whether it converges or diverges, even if I can't actually do the integral. So this function is certainly discontinuous at the origin. So I can't write discontinuous. That's better. This thing is definitely discontinuous at x equals 0. It's also discontinuous anywhere sine is 0. So it's also discontinuous when x is equal to pi, or 2 pi, or minus pi, or, so there's a plus or minus there, there's a plus or minus there. But I don't care about those, because the region of integration is between 0 and pi over 2. So between 0 and pi over 2, this thing is fine everywhere except 0. So it's discontinuous at 0, so we need to use our trick at 0, so we need to be thinking about other integrals near 0. Now, I do know some things about sine. One thing I know about sine, because my motivation here is maybe to try and get rid of the sine, because I've got this theorem that I might be able to use. And I know sine's between minus 1 and 1, so that tells me that x squared times sine is between, well, x squared and minus x squared. So I'm bounding sine. And if I know that x squared sine of x is between those two things, then I can concentrate on this and I can think about rearranging it. So if I divide this onto the other side and put it in the denominator, I'll get an x squared sine squared here. Oops, not sine squared, just an x squared sine. I'm taking this and dividing it on the other side, and I'll get a 1 over x squared there. In other words, I've shown that 1 over the thing we're interested in, the function we're interested in, x squared sine of x, that's, write it the right way around, that's bigger than or equal to 1 over x squared. Right, so let's think about what the graph must look like. I mean, I don't know what the graph of this thing looks like, But if I sketch the graph x squared, here's the graph x squared, I know, not x squared, sorry, I'm sketching the wrong function. If I sketch the graph 1 over x squared, which looks like this, what my argument is saying here is that 1 over x squared sine will always be bigger than that. So I don't know what it does, but it's there, right? There's the graph of 1 over x squared sine. So just intuitively, how does the area under the green curve compare to the area under the purple curve? Well, it's bigger, right? And we know something about 1 over x squared. So does this integral converge? Does the integral between 0 and pi over 2 of 1 over x squared dx converge? Well, look at the theorem. This is one of these p series, or p integrals, with p equals 2. If p is equal to 2, it's bigger than 1. So it diverges. So what that means is, intuitively, looking at the picture, that orange area is infinite. Right? I'm integrating from 0 to pi over 2 in this nice way, taking the limit, and I'm getting an infinite result. Right? In this case, p is 2, a is pi over 2. So I haven't written out the comparison theorem, but the comparison theorem we had last time is very similar. What I've shown, and this is what you need to show in these kind of cases, is that 1 over x squared sine of x is bigger than or equal to 1 over x squared everywhere on that interval. So in this case, on 0 to pi over 2. Well, actually not at 0 because it's not defined at 0, but you get the idea. From 0 to pi over 2. And we know that the integral from 0 to pi over 2 of that 1 over x squared by itself diverges. But the area we're looking at is bigger than that because the function is bigger. And so we can conclude that the integral between 0 and pi over 2 of this thing, 1 over x squared sine of x, also diverges. So we're done. That's all we needed. And in fact, if this diverges, then 3 times it must diverge, right? Because I'm just multiplying by 3. And if it's not finite to begin with, multiplying it by 3, it's not going to be finite. So this is a different kind of question than we've been asking. I want you to think about this because we're going to do a lot more of this kind of thought process in chapter 12, chapter 11, whatever the next chapter is. Maybe it's chapter 9, who knows. But we're going to be doing a lot more of this kind of process. You might not think about it as math in the way you've thought about it before, because what I'm doing is making a logical argument based on some, rules. I know how this p integral behaves. If p is bigger than 1, it's going to diverge. I know that the function I'm looking here is bigger than 1 on x squared everywhere. I know that the integral of 1 over x squared diverges, and so this, which intuitively must be bigger, will also diverge. All right, so let's finish this section with a couple more problems that kind of look at the big picture of what we've seen here. I took a break. That's why I've lost my glasses. All right. Here's an integral, the integral from -2 to 3 of this function. And notice that function, it's not continuous everywhere. And hopefully you can see it's not continuous at 1. Right? There's a 0 in the denominator. There's a vertical asymptote at 1. If we plotted the graph of that thing, it would look exactly like it has a vertical asymptote at 1, because it does. So there's the graph, and here's the vertical asymptote at 1. Which means we can't just integrate -2 to 3 and plug in. Because remember the fundamental theorem of calculus, we know how to do the integral, and then we plug in 3 and -2. But that only works if the function that we're integrating is continuous in that interval. And this is not continuous in that interval, so we have to break it into 2 pieces. And those 2 pieces are literally the integral from -2, where we start over here, until we get to 1. And then completely separately, the integral from 1 to 3. So those are completely different. So I'm going to make them different colors. Look how interactive this is. All right, so between 1 and 3, we've got the red region, and between -2 and 1, we've got the green region, and we've got to do them separately, which means each of them needs a variable introduced, and each of them needs to be integrated over a restricted region. So for example, I'm going to introduce an r here, and I'm going to integrate from -2 to r, and then take the limit as r goes to 1 from the left. And then separately, I'm going to introduce an r here. I'll make it straighter. An r there. A different r. Maybe I should call it s. I'm going to call it s. and I'm going to integrate between s and 1. And then I'm going to take the limit as s moves towards, I'm going to integrate between s and 3. That looked like a 1. And then I'm going to take the limit as s moves towards 1. And importantly, those variables are different, right? This limit is completely separate. This limit here is completely separate from that limit there. The thing that we're integrating is the same. The integrand is going to be the same in each case. But the limits of integration are different. And the limit that we then take after we've taken the limit of integration is different. So I've just integrated, each of these functions. And then I have to plug in, this is an s to 3. Right? We're integrating over this region, s to 3, and then separately we're going to integrate -2 to r, and then we're going to take those limits. And this is what you get. I've just plugged the r and the -2 and the 3 and the s, and then we need to take the limit formally, and looking at that, as r approaches 1 here from the left, so numbers a bit smaller than 1, r minus 1 is going to be negative, but this thing on the bottom is going to go to 0, but it's always going to be negative. So it'll be negative over negative, but increasingly small numbers in the denominator means that that whole thing goes to infinity. And similarly, looking at this one, when s goes to 1, but it's always going to be a bit bigger than 1, this is going to go to 0, but it's going to be positive, so that ratio also goes to infinity. So in both cases, you've got infinite area. It's not surprising, looking at the picture, they're symmetrical. We're going to get the same on either side, and in this case it's going to both be positive because they're positive areas, and they're both going to infinity. And so this integral diverges, and that's what we wanted to show. Either find that it converges and calculate the value, or show that it diverges. Alright, so I want to just comment here on what we couldn't do. Remember, we could have just gone ahead and found the antiderivative. The general antiderivative of this integrand is something like that, right? This antiderivative there. Imagine I just integrated that and calculated at the endpoints, -2 and 3. That would have given us some real number, right? I don't know what it is, but it's going to be some number. And it's definitely not infinite because it's a real number. So it disagrees with what we're seeing here. And that's because that fundamental theorem of calculus that says find the antiderivative and plug in the numbers, it only works when the function's continuous. And this function is not continuous between -2 and 3. It's broken at 1. It's discontinuous at 1. So the very fact that it's discontinuous at 1 says that this crazy stuff is not going to work in this case. Right? This fundamental theorem of calculus, it's great, but it's not going to work in this case because the function we're integrating is not continuous on the domain we're integrating it over. In other words, it's not continuous on -2, 3. If it was continuous on -2, 3, then yeah, do this. Plug in, right? Find the antiderivative, plug in the values. Great, if it's continuous. That's what we've added today. If it's broken somewhere in that region, then you need to do more. You need to break it up like this. All right, I want to give you one more example of a problem actually related to yesterday's lecture that I should have talked about yesterday, and then we'll call it a day. So this one asks us to find the integral of a function over what I'll call a doubly infinite region. Right, if I plot this function, 1 over 1 plus x squared, the function looks something like this. It's got its maximum at the middle, and then it goes something like this. Right, and so it goes off to infinity in both directions. Heads off to minus infinity, heads off to positive infinity. That area continues. So all of this area, under the curve, continues off to the left and it continues off to the right. And what I'm going to do is I'm going to break it up. I'm going to break it up and say that this is actually, because it's doubly infinite, I'm going to integrate it from minus infinity to some point in the middle, and 0 is as good a point as any. And then I'm going to go from 0 onwards to infinity. And that's going to give us that total integral. In other words, I'm going to integrate it, let's make that the orange, I'm going to integrate it from minus infinity to this point in the middle, which is 0. And you can choose any point, it doesn't matter, just pick a real number in between. Minus infinity, infinity. And then we're going to do the purple region. There's the purple region. There's the orange region. We have to do them separately. That's the important thing here. We can't do them together. You might think, well, let me write the next line. So here's the total limits of these things. What I'm doing is I'm introducing a value, let's call it r here, and I'm integrating up to r. So I'm integrating this yellow region, which takes me from, oh, sorry, I'm doing that completely wrong. Let me rephrase. I'm introducing a value r here, and I'm integrating from r to 0, and then I'm taking the limit as that r moves off to the left. And then on the other side, I'm introducing a value s here, and I'm integrating between 0 and s, and then I'm taking the limit as s moves off to the right to pick up all of that area that I've ignored. Right, so I'm doing those two separately. They're completely separate calculations and they need to be. What I mean by that is you should not do this. This assumes that there's symmetry. This assumes that I'm moving from the middle outwards in a nice, even, smooth fashion. I'm making assumptions that aren't true about the area. The area is just an area, right? Whereas integrating from minus r to r and then taking the limit as that single r goes to infinity is making assumptions about what I'm actually doing that aren't necessarily true. There's no reason I have to add up the area that way. It's adding up the area in a very neat, careful way that doesn't always have to be the way you add it up, because the area's got to be the area. So what I'm saying is, when you have a doubly infinite region like this, you need to split it into two regions, just like the previous example where we had a discontinuity in the middle and we needed to split it into two regions. Doubly infinite areas need to be split into two regions as well. And so let's integrate. And when we do the integral, remember this is bad, so never do this, I'm crossing it out. I'm using the fact that we know that antiderivative, 1 over 1 plus x squared, the antiderivative of that is inverse tan. So we've got that, and I've just plugged it in here and then plugged in the endpoints. And also we know that the inverse tan of 0 is 0, so we can just simplify this down to the limits. And here are the limits, and I notice there's a negative sign there, so I factored it out the front here. So I get this thing. All right. I'm sure you remember about inverse tan, right? We've talked about the inverse tan function this semester. Here's its graph. It goes wee. It's not a great inverse tan. It doesn't go up again there, and it doesn't go down again there. But it has, what are these things called? Horizontal asymptotes. That's what they're called. It has our horizontal asymptotes. So as x goes off to infinity in that direction, the tan function approaches pi over 2. As x goes to minus infinity in that direction, the tan function approaches minus pi over 2. So, sorry, the inverse tan function. This is the graph of inverse tan. So when we take these limits, we get, well, this limit was minus pi over 2. As it goes to minus infinity, the inverse tan is becoming minus pi over 2, and the other one becomes pi over 2. So these add to give us pi. This integral converges. We found the value. It was finite. That means that the integral converges. All right. So that's all I'm going to say about improper functions. Improper integrals. We've got the kind that has an infinity in the limit of integration. That's new. And then today we added the kind that have an unbounded function, a function that's discontinuous in the domain. And so have a go at some of the initial practice problems and the web work problems following on from this. I'm glad you've tuned in. I hope you've had a great day or night or evening or afternoon or whatever time it is that you're watching this. And tune in tomorrow. I'll see you soon.